Welcome to lesson 40. So in lesson 39, we decided to visualize the relationship between two quantitative variables. Now we're going to go ahead and fit a line to those data. So we're going to use the least square regression line, talk about what that means, and read some software output. So the least square regression line equation, so what we want to do, ideally, is we want to fit a line that is as close to all of the points as possible at once. And there is a way to optimize this. There's some beautiful or painful, depends on your view, like derivatives of matrices. We're not going to go there. We're going to do more basic, but know that R does it very, very nicely. So the model that best fits the line, we're going to describe it. So y hat is predicted. So anytime you see a hat, you should think, oh, well, this estimate comes from sample data. So using sample data, my estimated value for my response variable is equal to b naught, so that's a 0, so b0 plus b1 times x. So this is my explanatory. So each part, y hat. So the expected value for y, which is the response, given some particular value of x. So this might be the expected college GPA, given that someone had a GPA of 3.6, that kind of idea. B naught, or B0, that is our y-intercept, so the value of the y-intercept. So this is the value that we predict the response will be when x is equal to 0. Sometimes this makes sense, sometimes it doesn't. A lot of times we don't necessarily interpret it on its own. Depends on the scenario. B1, so this is our estimate for the slope. So the amount that y changes for every 1 unit increase in x. So x is our explanatory variable. So we leave x here, but we can plug in specific values. So I can plug in a specific, like if I want to plug in 3.4 into the linear equation for the GPA example, I could plug in 3.4 for high school GPA to predict what the college GPA would be for a student with a 3.4 in high school. So what do we mean by least squares? This is a little interesting. So you start off with your scatter plot, and it has all these lines. It's iterative process here. So what you do is you're going to calculate the sum of square errors. So you take this distance, and back in the day we didn't have the same computing power, so what we do to make sure that all of these distances, because what you observed minus what's predicted, here, that's going to be negative. Here, it's going to be positive. So to make them all the same sign, we square them. So then we have these squared differences. So if we can minimize these squared residuals here, we're going to have our best possible fitting line. So if we can simultaneously make this as small as these areas as small as possible, that'll be the line that fits simultaneously the points the best. So you can calculate it by, and we usually do not often do this by hand, take your observation 1 minus the predicted value for that observation, plus observation 2 plus minus the predicted value of observation 2, and square it and add all of them together. So here, when we minimize this sum of square error, we can calculate, and we put them in this order. It's very, very difficult to do in the other way. Our estimate for the slope is going to be our correlation coefficient times the standard deviation of the y values. So if you just take the y values and find the standard deviation of those, divided by the standard deviation of the x values. So take all the x values and take the standard deviation of those. That is your slope estimate. Your y-intercept estimate So you're going to take y bar, so you take all the y values, average them, minus, right here you have your slope estimate times x bar. So x bar is where you average all of your x values, multiply by your slope estimate. This is why you have to do it in this order, because if you don't estimate the slope value, it becomes really, really hard to do. It's still doable, but it's much more straightforward this way. So things to note is the way this is set up, the least squares regression line always passes through this point. It always passes through whatever x bar is as the next value, and then y bar. It will always pass through it because of how it's designed. Note here, remember I said that it doesn't matter so much the order for correlation coefficient? It absolutely matters which is which when you are putting them into the least square regression line. You absolutely must, because otherwise you're going to be predicting high school GPA based on what the college GPA is, and that's a different line. It will not fit these data. So calculating the least square regression line, these are rounded a little bit. So we have here, this is our high school data set. We have 10 observations. So if I wanted x bar, this is x, this is y, I'm just going to take those 10 high school GPAs, average them. If I want the standard deviation of x from the sample, just take those 10, find the standard deviation of those 10, do the same for y. We have a correlation coefficient. So looking here, remember we said about 0.82. It's a pretty strong relationship, positive linear relationship. So calculate the least square regression line. We're going to break into steps. So the first, I'm going to calculate the slope. So B1, and that's R times SY over SX. And if you're ever not sure which it should be, remember that slope is change in x over, change in y over change in x. Y is on top, x is on bottom. It should match because it's for slope. So here, I'm just going to plug in the values. So 0.817 times 0.288. It will absolutely matter if you mix up which is y and which is x here, because it will goof this part up. R will be okay, this part won't. Divided by 0.303. So I get something like 0.7766. I'm going to round it to 0.78. So that is my estimate for my slope. So I've done one step. My second now, I now want to find, what's my estimate for the y-intercept for this line. So that's going to be y bar minus B1 times x bar. I'm going to put parentheses here, it just makes me keep track to do the multiplication first. So 3.44 was y bar minus this 7.8 that I just calculated times x bar is 3.55. And I get something like 0.671. Once again, I use some rounding here. So I haven't quite answered the question, almost. I have the components, but I must put them together. So step 3, y hat is equal to B0 plus B1 times x. That's going to be y hat is equal to, I'm going to round here, 0.67 plus, this was positive, 0.78 times x. Something that's important, I would indicate x is high school GPA, y hat is college GPA. That is something that if you give us an an equation with y hat and x and you don't label what they are, we will absolutely, it's worth something. It's not worth most of the points, but it is something that we do look for. So you should use labels so we know which variable's which. And this organization is actually really useful because later it'll say, hey, if I have a high school GPA of this, what is my estimated college GPA? And you know exactly where to plug it in. Sometimes the reverse. They might say, hey, I had a college GPA of this. From this line, what do you estimate their high school GPA was? But that's less often. So once you have this least square regression line, we interpret the parts. So you have the y-intercept, which you absolutely are free to look at. So it's not always necessary. In fact, sometimes it doesn't make sense. And you should note that there are times it won't make sense. So only interpret it if it does make sense to predict the response variable when y is equal to 0. Because not all explanatory variables make sense when they're equal to 0. So, for instance, I had a data set. It was, they were like newborns, so it was like baby length in, I don't know, centimeters, and baby weight in, I don't know, grams. And they had something like this, and it didn't make sense to say, hey, this is the predicted baby weight when the baby is 0 centimeters long, because a baby that's 0 centimeters long doesn't exist, right? It's not there. So it doesn't make sense. You definitely, there are definitely scenarios it will not make sense to interpret the y-intercept. And then the slope, this is something we usually are very interested in interpreting. So we talk about for a 1 unit increase in x, so whatever that is, if it's high school GPA, that's a 1.0 increase. The predicted value of y, we'll want to know what y is expected to change by whatever the slope is. So if you have a positive slope, we think, oh, well, our estimated value for y is going to increase when you increase x. If you have a negative slope, you estimate that it'll decrease. If on the weird occasion you get that that b is equal to 0, this is saying that knowing y, there's no change in, knowing x, there's no change in y as far as what we're predicting. Knowing x gives me no additional information about what y is, that kind of thing. And we're going to get into that probably more on Thursday, what that really would mean. Basically, it means fitting a flat line is fine. Ideally, though, if you think an explanatory variable is useful in predicting the response, you really don't want this third thing to happen. It doesn't mean it doesn't. You just don't want it to. So there is a general format. So seriously, if you have to, if you have these printed out or whatever you're doing on these, you want to mark that other page with the template that described the relationship between the two variables. You're going to want this one too. So here, our format, the least square regression line estimates that for every, so whatever one unit increase is in explanatory. So for GPA, for every 1.0 increase in GPA, so in GPA, whatever your response variable is in context is estimated to increase or decrease, so this depends on the sign of B1, by whatever your slope is and your units for the response variable. So on average. So absolutely, we're going to look for this. We want to say, hey, for every 1 unit increase in x, we're going to look for that, but it needs to be in context. We're going to need to know that you think the response is going to change and by how much, and will it decrease or increase. We will look for that every time. So for example, we're going to throw the high school GPA example at y'all. We use slightly different roundings, so the computer, it rounds out to 0.69 and 0.78. So here, our least square regression line, looking at a slope of 0.78. For every 1.0 So 1.0 increase in high school GPA. The first year college GPA is expected to increase by 0.78 points on average. Also note, I didn't write it so that I say that increasing at 1.0 in high school causes this change. You don't want to write that language. You want to avoid the causal language unless you know it was a randomized experiment, and most of the time we will not have that here. So for example then, this is my slope. If I want my y-intercept, so now I'm looking at the 0.69 for a student with a high school GPA of 0.0. We predict a college GPA, so that first year college GPA of 0.69. So if we have a high school student with a 0.0 GPA, we predict their college GPA is 0.69. This doesn't really make sense though, because chances are there are not going to be too many high school GPAs of 0.0 that get into the college right off the bat. So I would argue that this interpretation, it doesn't make sense to actually look at. But every once in a while, whatever your explanatory variable is, it can make sense to actually look at when it's 0. But for GPA of zeros, not so much, especially since what we observed in our samples, not even close to 0. It's all 3 point something to 4.0. It won't make sense here. So now we're going to look at reading statistical software. So here, this will say intercept. In R, I think a lot of the times it'll put a parentheses, but this always goes with the y-intercept. And then whatever the name of your explanatory variable, this is saying, oh, well, this is the slope that goes with this explanatory variable. So this would be output from R. So formula, so this is my response by, so tilde, by my explanatory. So here, looking, this is where we want to focus. If I want to put together the equation in my line, so I'm just going to pull from here. So my y-intercept, before we wrote 0.69, 0.8, sorry, talking and writing can be hard. 0.6861. Before we put 0.69, in general, always make sure that you have at least 2 places past the decimal. If we specify more, definitely put more. We will get you if we say we want 4 and you give us 2. That is a thing. A lot of times it's intentional because we know that until you like square root things look really, really small. Plus, so this is B0, this is B1, and I'm just going to plug that straight in, 0.7758. And then y hat is predicted or estimated college GPA, and x is equal to high school GPA. I really cannot stress enough, please include your labels. It's really important. You can, right? So the hat means predicted. We will always look for the hat here. It should have a hat. If you're using output in R from a sample, there should be a hat. So you could put hat college GPA, I should have probably written college GPA first, is equal to 0.69 plus 0.78 times high school GPA. That would be okay. But if you use the generic y, hat, and x, you must label them. Really, really important. As for the rest of this, we're going to get to it, just not yet. So here, Now that we have this line, one of the really, really popular things that we do with it is we like to make predictions with it. So suppose I have a first-year college student and they have a high school GPA of 3.6. Suppose I want to estimate or predict what their college GPA would be. So right here, 3.6, I'm looking at where it meets the line and then finding this y hat value. So I will plug into here. So remember, y hat is predicted college GPA. X is equal to high school GPA. Sorry, my G's are looking goofy. So what I know, I have a 3.6 high school GPA. I know X, so that means I'm going to plug it in for X. So y hat is equal to 0.69 plus 0.78 times 3.6, because that was an X value. Go ahead and do the math. Just remember, I know this probably seems like, oh no, the order of operations, multiply first, then add. Otherwise it will go sideways. So looking here, I end up getting, this is not math I can do on my own, I gotta check. I end up getting 0.69 plus 2.808 comes out to 3.498. So our least square regression line estimates a 3.498 first year college GPA for a student that had a high school GPA of 3.6. So I cannot write as fast as I'm talking here. So there we go. If we have a high school GPA student of 3.6, for a student with, wasn't quite a sentence there. So least square regression equation estimates it's 3.498 first year college GPA for a student with a high school GPA of 3.6. So while this line's increasing, you might notice that the slope is less than 1, so it's not quite increasing. Like if you have a 3.4 in high school, it estimates you'll get a little bit lower than a 3.4 in college. That's what this is estimating. Same here. 3.6 in high school. It's a little bit less than 3.6 in college. But this is my estimate. So from there, we're going to start talking about conditions. That's lesson 41. We'll see you there.